The topic of our lecture today is bioacoustics, elastic waves, the Doppler effect. The physical phenomena and processes that we are going to consider with you today are close to each of you, since repetitive processes continuously occur inside any living organism. For example, the work of the lungs, the contraction of the heart. When we are cold, we shiver. We hear and talk thanks to the vibrations of the eardrums and vocal cords. When we walk, our legs also make oscillatory movements. The atoms of which we are composed are oscillating. Today at the lecture, we will look at several sections: mechanical vibrations and waves, sound, ultrasound, and the Doppler effect. Application in medicine. The field of physics that studies elastic wave vibrations, as well as methods of their reception and registration, their interaction with matter, and various applications, is called acoustics. Acoustics is also a branch of physics in which sound phenomena are studied. Biological acoustics is a science that studies sound-emitting materials. Sound-perceiving human organs. The problem of speech formation, perception, sound transmission, and the effect of sound and vibrations on biological objects. Let's look now what fluctuations are. Oscillation is a process or movement that is characterized by a certain degree of repeatability over time. Inside any living organism, various repetitive processes continuously occur. For example, the work of the heart and lungs, and all these phenomena obey some general laws. Types of fluctuations. The types of vibrations are distinguished by their physical nature. These are mechanical, thermal, electrical, and by the nature of the interaction of the oscillating system with surrounding bodies. Free, harmonic, damped, forced self-oscillations are distinguished. Free intrinsic mechanical vibrations are vibrations that occur without change in external action due to the energy initially received by the body. Free oscillations include harmonic and damped oscillations. Models of such oscillation data are, for example, a spring pendulum, that is, a body suspended on a spring, and also a mathematical pendulum is a body suspended on a thread. Let's consider the simplest type of oscillation. This is a harmonic oscillation, in which the displacement from the equilibrium position changes over time, according to the law of sine or Cassini, without taking into account the action of resistance forces. Analytically, the regularity of the shift change in time for harmonic oscillations is expressed by the following formula, which I have written on the slide. X equals a multiplied by the Cassini, omega 0 T0. The graph of harmonic oscillations will be, respectively, a sinusoid or a Cassini, and just on the slide shows a graph of harmonic oscillations in which the displacement from the equilibrium position x is shifted in time according to the law of sine or Cassini. Now let's look at the characteristics of harmonic oscillations and the characteristics of harmonic oscillation. The first is the amplitude denoted by the letter A. This is the maximum deviation from the equilibrium position. The unit of measurement is measured in meters. The amplitude is determined by the properties of the oscillatory system. And also the initial conditions, that is, the positions, the speed of the body at a time. The ideality of a harmonic oscillation is that the amplitude of harmonic oscillations does not change over time. You see, the amplitude is equal to a constant. The next characteristic of a harmonic oscillation is the period. Denoted by the letter T, the unit of measurement is seconds. This is the shortest period of time for which one complete oscillation is performed. The next characteristic is the circular frequency, omega 0, the number of oscillations performed in 2 seconds. This oscillation characteristic depends only on the properties of the oscillatory system. The next characteristic is phi 0. The initial phase of the oscillations is measured in radians. It depends only on the initial conditions, that is, on the position of the velocity of the body at a time. The next one is cyclic purity. This is the number of oscillations performed per unit of time. Denoted by the letter nu, the unit of measurement is duke or seconds minus the first degree. And another characteristic is the oscillation period. It is denoted by the letter T and is determined by this ratio. 1 divided by it, or 2 divided by omega 0. Look, fluctuations are a process that takes place over time. And what is a wave? Let's present such an example. Let's take a long cord, and behind the crepes, and one end of it, and bring the other into oscillatory motion. What will we see? That something is running along the cord, although the ends of the cord remain in place. What runs along the cord is a wave. And this kind of waves are called running waves. Therefore, look, a wave is a process propagating in the medium, in time and in space. In other words, a wave is the propagation of vibrations from point to point, from particle to particle. A mechanical wave is a phenomenon of propagation of a mechanical oscillation in a medium with energy transfer. Due to the presence of an elastic bond between the particles of the medium, the movement of one of the particles, when vibrations occur, causes the movement of neighboring particles. This process propagates in space with some speed. And so, when a mechanical wave propagates, the particles of the medium themselves do not move with it, but oscillate around their equilibrium positions. Therefore, the wave propagation is not accompanied by a transfer. Substances. There are longitudinal and transverse waves. Two types of waves, that is, waves propagating in a direction perpendicular to the direction of vibration of particles in the wave, are called transverse. And a wave in which vibrations occur along the same straight line as their propagation is called a longitudinal wave. Also characterizes the wavelength. In other words, it is the distance between 2 points whose phases differ by 2 pi at the same time, and is equal to the distance traveled by the wave during the oscillation period. Since the speed of wave propagation depends on the properties of the medium, the wavelength changes during the transition from one medium to another, while the purity remains the same. Once again, everything out there transfers energy without transferring matter. Let's look at the energy characteristics of the Volga. In other words, for a quantitative description of the energy transfer, it introduces the following characteristics. The first is the flow of wave energy. The energy flow of a wave is the amount of energy that is carried by a wave through a certain area per unit of time. The unit of measurement is joule per second or watt. The energy density of the wave. The second characteristic is the density of the wave energy flow, or in another way, we can say it is the intensity of the wave. This is the flow of wave energy related to the surface area, located perpendicular to the direction of wave propagation, of the unit of measurement watts per meter squared. Sound research methods in medicine. Man lives in a world of sounds. Sound is what the ear hears. We hear the voices of people, the singing of birds, the sounds of musical instruments, the noise of the forest, a thunderstorm during thunder during a thunderstorm, the noise of students at a lecture. What is sound? How does it arise? How do some sounds differ from others? We know that sound is a wave. A special case of mechanical wave vibrations is sound wave vibrations. In other words, look, sound is a mechanical wave propagating in a medium with a frequency from 16 Hz to 20,000 Hz. Sound has objective characteristics that are inherent in any wave, and subjective characteristics that are determined by a person's perception of sound. The objective characteristics of sound include purity, sound wavelength, sound speed. Well, let's, for example, talk about the speed of sound, and let's talk what we know about the speed of sound. Like any wave, a sound wave is characterized by the speed of propagation of vibrations in it. The speed of sound is different in different environments, so in the air at a temperature of 20 degrees Celsius, the speed of sound waves of any limbo is approximately 340 meters per second. In water, 1,500 meters per second, and in a solid body, more than 2,000. Objective characteristics include energy characteristics, right, which you see. This is the density of the energy flow of waves, or we call it the intensity or strength of sound in another way. Sound or acoustic pressure, an additional pressure that is excessive above the average ambient pressure that is formed in the study areas of particles in a sound wave. The units of sound pressure are pascals. And the spectral composition of sound waves, that is, the spectrum, a set of wave frequencies indicating their intensity and amplitude. This is the acoustic spectrum. According to the spectrum, the following sound vibrations are distinguished. The first is the tone. The tone happens. A tone is a sound that represents vibrations with constant or periodic varying amplitude and frequency over time. The tone can be simple or complex. A simple tone is a simple harmonic oscillation. For example, a tuning fork sounds. A complex tone is a combination of several simple tones. This, for example, can be the speech of a person, the sounds of musical instruments. A complex tone can also be decomposed into simple ones. The tone has a linear spectrum. The second is noise. This is a sound characterized by a complex, non-repetitive time dependence. It has a solid aspect. Noise is a chaotic mixture of tones. The noise of the crowd, the noise of students at the lecture, and a sonic boom. A sonic boom is a short-term strong sound effect. But it can be, for example, a clap, a bang, an explosion. The sonic boom has a continuous spectrum. At the very beginning, I said that there are subjective and objective characteristics of sound. Subjective, in another way we can say physiologically objective, physical. That is, physical, objective, physiological, subjective, physically objective purity, harmonic spectrum, intensity. Now let's move on to subjective characteristics. This is the pitch. Pitch is a subjective characteristic that is determined by the frequency of the pitch. In other words, the higher the frequency of the sound, the higher the sound is perceived. To a large extent, to a lesser extent, the pitch depends on the complexity of the tone and on its intensity. Timbre is a subjective characteristic that depends on the spectral composition of the sound. Timbre, we can say that it is a sound coloration, and loudness is a subjective characteristic of sound that characterizes the auditory sensation for a given sound. It can be quantified by comparing the auditory sensation from two sources. Mathematically, the units of volume are dB, decibels, backgrounds. Mathematically, it is written down at the very bottom of your formula. This is Weber-Fechner's law. Weber-Fechner's law. In other words, we can quantify the volume, the subjective characteristic, using this law. At the heart of the creation is Weber-Fechner's psychological law. Mathematically, this means that the volume of sound is proportional to the logarithm of the sound intensity. That is, the strength of the auditory sensation. Sensation is proportional to the logarithm of the ratio, the power of sound to the threshold of audibility. Weber-Fechner's law sounds like this. If the irritation is increased exponentially, that is, by the same number of times, then the sensation of this irritation increases in arithmetic progression, that is, by the same physical amount. On the same, just the size. Let's see the volume levels, right? The normal human ear perceives a fairly wide range of sound intensity, and it is more convenient to use a logarithmic intensity level scale, since the ratio of the two intensities is usually a very large number. The scale would be cumbersome, very large. So what do we see here on it? The intensity of the minimum threshold for human sound perception is equal to 10 minus the 12th watt per meter squared, taken as 0 decibels. The sound is 10 times more powerful and has an intensity level of 10 decibels. A million times 60 decibels, 10 million times 130 decibels. 130 is a sound that already hurts. And for 1 bell, it takes the level of sound intensity, the intensity of which is 10 times greater than the threshold of audibility. The volume level is also expressed in the backgrounds. It is generally assumed that at a frequency of 1 kilohertz, the scale of the volume scale and the intensity levels coincide. That is, there is a unit of the sound intensity level scale, corresponding to a tenfold change in the intensity level. There are several. You can give several values of the sound intensity level. This is, for example, a whisper at a distance of 1 meter, approximately 20 decibels. A normal conversation is about 50 decibels. A scream is about 80 decibels. The plane's engine is 130 decibels. And so, as I told you, the pain sensation is about 120 decibels. Now let's look at sound research methods in medicine. Briefly, audiometry is a method of measuring hearing acuity using a special audiometer device that determines the points of the hearing threshold curve at different frequencies. The resulting curve is called an audiogram. Audiograms of a sick person are compared with the normal curve of the audibility threshold. This helps to diagnose diseases of the hearing organs. Sound can be a source of information about the state of a person's internal organs. Therefore, the next sound research method is auscultation, a method of listening with a stethoscope and a phonoendoscope. The next method of cardiography background is a method of graphical registration of heart tone and noises. Another method is percussion, a method of listening to the sound of individual parts of the body when tapping. Analysis of the resulting sound. Ultrasound is also widely used in medical practice. Let's look at the diagram. In general, elastic mechanical oscillation of a wave with a frequency of less than 16 Hz, IDS from 0 to 16 Hz, is infrasound. These are sound waves that have a purity lower perceived by the human ear. Speaking of which, well, okay, we're not going to talk about infrasound. The next one is a sound from 16 Hz to 20,000 Hz. It's a sound, and elastic mechanical vibrations of a wave with a frequency of 20 to 10 tenths of Hertz is called ultrasound. In other words, the upper bound of ultrasonic frequencies is determined by intermolecular distances, and therefore depends on the aggregate state of the substance in which the ultrasonic wave propagates. In general, ultrasound sources are divided into artificial and natural. For the artificial generation of ultrasound, various types of ultrasonic, technological, and medical equipment are used. Ultrasonic devices refer to artificial sources of ultrasound with equipment, during the operation of which ultrasonic vibrations occur as a concomitant factor. In nature, ultrasound is found as a component of natural noise, that is, the noise of wind, rain, waterfall, lightning discharges, and among the sounds of the animal world, dolphins, bats. Some animals use ultrasonic waves to detect obstacles, orient themselves in space. For example, bats. In its physical essence, Ultrasound does not differ from sound since it also represents a longitudinal mechanical wave. However, ultrasonic waves have their own characteristics. The first is that the ultrasound wavelength is significantly less than the sound wavelength. For example, in water, for sound with a frequency of 1 kHz, the wavelength is 1.5 meters, and for ultrasound with a frequency of 1 MHz, the wavelength is 1/5 of a millimeter, and for ultrasound with a frequency of 1 GHz, the wavelength is 1/5 of a micrometer. Due to the small wavelength, the reflection and diffraction of ultrasound occurs on objects of smaller dimensions than for audible sound. That is, under certain conditions of small size of obstacles, the ultrasonic wave propagates in a directed flow. And when ultrasound passes through a substance, its significant attenuation occurs due to absorption, which is due to its small wavelength. The absorption depth varies for different tissues. It depends on the intensity of ultrasound and the density of the medium. Ultrasound is strongly absorbed by air. In the liquid environment of the body, for example, blood, the absorption of ultrasound is much less than in soft tissues, and even more so in bone tissues. Now let's take a look. Biophysical effect of ultrasound on matter. The complex biophysical effect of ultrasound on matter includes several types of actions: mechanical, for example, thermal, and chemical. Let's look at the mechanical. The compression and resolution created by the ultrasonic wave leads to the formation of discontinuities of a solid liquid and the formation of cavities in it. This concept is called cavitation. Cavitation does not exist for long and quickly closes, that is, energy is released and substances are heated. Substances ionization. The cavitation process leads to mixing of the components of the cellular cytoplasm and changes in viscosity, which in turn causes significant changes in cell functions. Ultrasound can detach biological molecules from cell membranes, change the surface charges of the membrane, their permeability, thereby affecting the vital activity of strong ones. With a sufficiently high intensity of ultrasound, the membranes are destroyed. With the propagation of ultrasound, deformations develop in the substance. Depending on the intensity of the wave, these deformations can cause either minor changes in the structure or destroy it. Ultrasonic vibrations are able to soften the particles of the medium, mixing them and forming emulsions. If the intensity exceeds the cavitation threshold, the ultrasound intensity exceeds the cavitation threshold. Then the destruction of microorganisms is observed, in particular, the destruction of the available liquid of bacteria, viruses. Therefore, microcavities are formed in the liquid, once again in the liquid at the moment of stretching, which are filled with liquid vapors, and this phenomenon is called cavitation. That is, once again, they do not exist for long in microcavities, and at the moment of slamming, releases energy that can be so large that it will cause ionization, dissociation in the surrounding molecules. Therefore, the mechanical effect of ultrasound is used, how to crush and disperse various media, that is, for the manufacture of vaccines, emulsions. The next biophysical effect of ultrasound on matter is thermal. Another effect of ultrasound associated with the processes of heat formation in a medium exposed to ultrasonic vibrations. The formation of heat is determined by the amount of absorbed energy of ultrasonic vibrations, proportional to the frequency of vibrations, the viscosity of the medium, and its thermal conductivity. So the thermal effect at a depth of 2 to 5 meters with ultrasound irradiation at 40 kilos of watts per meter squared for 20 seconds leads to an increase in the temperature of the body tissue by 5 to 6 degrees. Heat is released mainly at the interface of a fabric with different acoustic resistances, or in the same fabric, on inhomogeneities of its structure. That is, local heating of the tissue increases the intensity of metabolic processes, but prolonged exposure can lead to overheating. And the next biophysical effect of ultrasound on a substance is chemical. The chemical effect of ultrasound on a substance can be attributed to the activation of water, that is, the splitting of water molecules into hydrogen radicals and the subsequent formation of hydrogen peroxide ash to O2, as well as the acceleration of oxidation and diffusion processes. Prolonged systematic exposure to ultrasound, which is distributed by air, causes changes in the nervous cardiovascular endocrine system of the auditory stimulatory analyzers. In general, ultrasound has a local effect on the body as it is transmitted by direct contact with an ultrasonic instrument, where ultrasonic vibrations occur. Let's now look at the methods of generating ultrasound. There are the following main methods for obtaining ultrasonic vibrations based on the inverse piezoelectric effect, on the basis of the Sagittarius magnet, and on the basis of electrostriction. To generate ultrasound, a device called ultrasonic emitters is used. Ultrasonic emitter based on reverse piezoelectric effect. The most common reverse piezoelectric effect is the mechanical deformation of bodies under the action of an electric field. The main part of such an emitter is a plate made of a substance with well-defined piezoelectric properties, for example, quartz, ferritic salt. Electrodes are applied to the surface of the plate. If an alternating electric voltage from the generator is applied to the electrodes, the plate, due to the reverse piezoelectric effect, begins to vibrate, emitting a mechanical wave of the appropriate frequency. The amount of deformation of the plate will be proportional to the voltage of the generator. The frequency of forced plate vibrations, compression and stretching depends on the frequency of voltage changes. Thus, the quartz plate, vibrating, will emit an ultrasonic wave, a wave of the appropriate frequency. The next other ultrasonic emitter is a magnetostriction-based emitter. Magnetostriction is a change in the length of elongation or shortening of the fur of a magnetic rod placed in a high-frequency alternating magnetic field. That is, inside the winding, through which an alternating current flows with a frequency of changing the direction of the field. Vibrations of the ends of the rod will create an ultrasonic wave in the medium, and another emitter is electrostriction. The phenomenon of electrostriction consists in changing the size of some materials, these are ceramic insulators, in an alternating electric field. This phenomenon is caused by the polarization of the dielectric in an electric field. The propagation features and characteristic properties of ultrasound determine its use in medicine. Look, here we have ultrasound diagnostics, ultrasound in therapy, and ultrasound in surgery presented on the slide. In other words, ultrasound waves of various intensities are used for medical purposes. In diagnostics, this is a small one. In therapy, the average, well, and one might say in surgery, the intensity is high. Pay attention to the intensity. The intensity of ultrasound and ultrasound also determines the area of medicine where it needs to be applied. Ultrasound is used for imaging in medical diagnostics because it has the ability to penetrate into the human body and interact with biological tissue. In diagnostics, ultrasound is used to examine hard-to-reach organs, as well as to detect pathology. These methods are based on the peculiarities of ultrasound propagation at the boundaries of two media. Well, let's see the ultrasonic location. Ultrasonic location. Work continuously. There is a continuous pulse mode. The continuous mode uses a standing wave with interference of the incident and reflected waves from the interface of the media. The pulse mode registers pulses reflected from the boundary of means with different acoustic resistance and replaces the propagation time of ultrasound to the object under study and back. Knowing the speed of ultrasound propagation determines the depth of the object. This method is called a diagnostic echometer, the echo method, allows you to differentiate soft tissues that differ in density by only 0.1%. This method is similar to radiography, but the images of two tissues on an X-ray differ from each other, only if their densities differ by at least 10%. In addition, low-intensity ultrasound is practically harmless to living beings. It is impossible to say about X-ray radiation, and ultrasound equipment is more complex and cheaper than X-ray. The next ultrasound screening. Ultrasonic transmission is based on the absorption of ultrasound by tissues with various acoustic properties. In this case, the sensor, the receiver that has passed the ultrasonic wave, is placed behind the object under study, and according to the change in the intensity of the transmitted ultrasound of the reproducer, the shadow picture of the internal structure of the object. A shadow picture of the internal structure of objects is reproduced. Echography. I'm sorry, this is the definition of a brain tumor using ultrasound. Ultrasound, ultrasound cardiography, measurement of the size of the heart in dynamics. For diagnostic purposes, it is important to know the maximum and instantaneous value of the velocities of the heart walls with a time sweep. It is these parameters that can be obtained by the Doppler method, which allows recording Doppler frequencies caused by the reflection of ultrasound from moving parts of the heart. There are existing installations can measure the distance to the areas of the heart, their dimensions, acceleration rates, record the beginning and duration of various phases of the cardiac cycle. The next ultrasound therapy, pay attention again to the intensity. This is the treatment and prevention of human diseases with the help of ultrasonic vibrations. The therapeutic effect of ultrasound on the human body is due to the combined action of a number of factors. Est mechanical vibration of the tissue, effects of a physicochemical nature, as well as heat, that is released when ultrasonic energy is absorbed in the tissues. Ultrasound is a kind of catalyst that accelerates the establishment of an equilibrium state of the body from a physiological point of view, that is, a healthy state. At the same time, ultrasound has an effect mainly on patients and not on healthy tissues. With the mechanical action of the ultra-tooth, the diffusion process is stimulated, metabolism is enhanced, and microcirculation is improved. And ultrasound surgery. Ultrasound surgery is based on the use of ultrasonic vibrations to destroy biological tissues. Two ultrasound methods are used in surgery. The first one is based on the destruction of the body tissue by ultrasonic vibrations proper. The second one is associated with the imposition of ultrasonic vibrations on a surgical instrument. In the first case, both direct contacts of the ultrasonic emitter with the tissue and exposure to tissue with focused ultrasound are used. The use of focused ultrasound is particularly appropriate for creating local destruction in the deep tissues of the body. For example, the structure of the brain. The destruction of tissues under the influence of focused ultrasound is associated with two factors: the heat that is released when ultrasound is absorbed by tissues and the phenomenon of cavitation, which we have considered. Depending on the chosen intensity of ultrasonic vibrations, one or another factor has a predominant effect. Ultrasound is used in surgical operations involving the connection of broken or intentionally dissected bones during surgery. During these operations, the space between the broken bones is filled with bone chips mixed with liquids, liquid plastics. For example, cyacrine. Sound vibrations contribute to a deeper penetration of cyacrine into the pores of bone tissue, and cause its accelerated polymerization, as a result of which a reliable connection of fragments is formed for the period of natural processes of bone regeneration. The use of this surgical method allows, in particular, to avoid the use of metal structures that need to be removed from the body during repeated operations. Ultrasound is also used in dentistry. Ultrasound treatment is used in a dental clinic for a number of diseases with the help of ultrasound dental instruments. It is possible to form various more effective and painless. Various cavities, remove dental stones, perform cutting operations. Doppler effect, the Doppler effect, and its application in medicine. In 1842 year, Christian Doppler discovered an effect that was named after him, the Doppler effect. What is the Doppler effect? This is a change in the frequency of waves. We perceive them as the receiver of the observer's waves when the wave source and the observer move relative to each other. It can be observed in optics acoustics and also used in medicine. You can see on the slide the general formula, where it's the frequency of the wave emitted by a source moving at speed. Descended by the source. Nu is the speed of the wave. The non-stroke is the frequency of the wave perceived by the observer, moving at the speed of the observer. Nu is the speed of the wave. There are upper and lower signs there. Upper signs for the case of convergence, lower signs for the case of removal. Here, please, in your picture, when the observer's wave source approaches, the perceived purity is greater than the emitted one. And when the wave source and the observer are removed from each other by perceiving the frequency. The perceived purity is less than the emitted one. The Doppler effect can be used to determine the speed of movement of the body in the environment, in particular in medicine, to determine the speed of blood flow, the speed of movement of the valves and the walls of the heart. Doppler echocardiography. In medicine, this formula is used to determine the rate of red blood cells. The erythrocyte velocity is approximately equal to the ratio of the product of the ultrasound velocity by the Doppler frequency shift and divided by the initial frequency 2 times the initial ultrasound frequency. The figure shows a diagram of the installation for measuring blood velocity. The generator emits an ultrasonic wave with a frequency that propagates in the medium at the speed of sound, ultrasound. Blood is moving towards the wave. The ultrasound generator here performs the role of a stationary source, of a moving erythrocyte as a receiver. Ultrasound reflects, that is, now the red blood cell is a source, a technical system, a stationary receiver. The incident reflected ultrasonic waves are compared. The resulting frequency difference is called the Doppler frequency shift. Just here it is, the Doppler frequency shift formula. The main advantage of this method is that it is non-invasive. That is, the measurement is carried out without violating the integrity of the vessel. An echometer based on the Doppler effect is beginning to be particularly widely used, which makes it possible to study not only the location of certain areas of tissue, but also the physiological processes in their dynamics. Doppler echodopplerography. The use of the Doppler effect makes it possible to determine the cancer of blood flow parameters in the vascular system. That is, I repeat, the speed of blood flow, the speed of movement of the valves, the heart, the rate of oscillations, the walls of the heart, ultrasound reflection from pulsating vessel walls, and plasma-suspended shaped blood elements moving with it, mainly from red blood cells, the acoustic resistance of which differs significantly from the acoustic resistance of blood plasma. Accompanied by the Doppler effect. Knowing the Doppler frequency, you can use the formula to calculate the speed of movement of red blood cells, and therefore the speed of blood flow, by Doppler signals formed by the outer and inner walls of the vessel. It is possible to determine the diameter of the vessel, and by signals from red blood cells, to find out at what distance from the vessel wall there are red blood cells with a certain speed. This makes it possible to study the dynamics of blood flow in different sections of the vascular cross-section. The method of ultrasound arteriography, which allows obtaining a two-dimensional image of blood flow, is particularly interesting and promising. The Doppler sensor attaches to a lever that can be moved manually or with the help of a special device along the blood vessel, while simultaneously moving it in a plane perpendicular to the axis of the scanning vessel. This concludes my lecture. Thank you for your attention.